on II open sets. It is a well-known fact that modern topologists recognize many families of subsets which have weaker properties than standard open sets. For example, we may mention alpha, semi, pre, beta, or B open sets. And their definitions were presented in our earlier videos, so we shall not repeat them here at this moment. As for the II open sets, they've been introduced by Amir Mohammed and Beda Abdullah in 2019. In fact, they can be considered as an extension of the idea of I open sets, which have been presented by Amir Mohammed and Sabi Askandar a few years earlier. Let us recall the very definition of I open set. We say that a subset A of a topological space X with topology tau is I open if there exists an open set G different than empty set and different than the whole universe, such that A is contained in the closure of A and G, of the intersection of A and G. The complement of an I open set is called I closed set, of course. Now let us go further. We say that A contained in X is I open if there exists an open set G different than empty set and the whole universe, such that A is contained in the closure of the intersection of A and G, and this is the idea of I open set, but we have this additional condition. Interior of A is equal to G. We have also int open sets. A is int open if there exists an open set G different than empty set in the whole universe, such that G can be considered as interior of A. For example, let X be A, B, C, three elements. Very simple, finite universe. And our topology consists of the empty set, the whole universe X, the singleton of B, and this set which contains B and C. The set of closed elements, or complements of open sets, is the empty set, X, AC, and A. And now we have the following families of int open sets, I open sets, and II open sets. They are listed here. Of course, you should assure that these calculations are true. Note that, for example, AC is I open because there is G, namely BC, such that AC is contained in the closure of the intersection of AC and BC, hence in the closure of the singleton of C. But this closure is precisely AC, because AC is closed, and for this reason it is the smallest closed set in which C, singleton of C, is contained. And of course, AC is contained in itself. But on the other hand, AC is not II open. It is I open, but not II open, because interior of AC is empty, as there is no open set contained in AC, as we can see here. An empty set clearly is different than G, namely BC. One can prove that every open set is II open set, and the converse is not true. Every II open set is I open and int open, and the converses are not true, of course. And that every alpha open set is II open, and converse is not true. These theorems are in the original paper of our authors, namely Mohammed and Abdullah. The following theorem is important and it has also been proved by our authors. If we have a topological space, then the set of II open sets on X is also a topological space. So they have these sets, II open sets, they have all the expected properties of topology, closure under finite intersections and closure under arbitrary unions, and so on. Further studies on the theory of II open sets have been already developed. For example, Kumar investigated II separation actions. He defined them in a manner similar to the one known from the theory of typical separation actions. Kumar and Sharma studied II regular spaces, and recently Abdullah and Mohammed introduced II open sets in B topological spaces. So in the spaces with two topologies. And this last idea should be mentioned here, at least briefly. Let X with topologies tau1 and tau2 be a B topological space. Then A is called tau1, tau2 II open set if there exist two sets U, V, both different than the empty set and the whole universe, such that each of them is open at least in one of these topologies, so U, V, they both belong to the union of tau1 and tau2, and A is contained in closure with respect to topology 1 of the intersection of A and U, or is contained in closure of A of the intersection of A and V. Analogously, A should be an interior of U, or A should be an interior of V, here with respect to topology tau1 and here with respect to topology tau2. Well, for example, consider this universe ABCD and these two topologies on this universe, tau1 and tau2. One can show, after some calculations of course, and you should perform them, that tau1, tau2 II open sets in this universe, in this B topological space, are namely these ones: empty set X, singleton of A, singleton of C, AC, and finally BCD. And this is our bibliography, these are our references. Thank you very much for your attention.